Often in your work you're going to want to be able to describe a graph in words. Many times you'll have data sets or you'll construct graphs of different functions, one thing or another, but you will have graphs that you need to describe. And there are certain behaviors of graphs that allow us to do a pretty good job of describing the behavior of a graph. For example, right here we have a straight line. Okay, so we would say that this function is linear and increasing. We could say that it has a y-intercept. If we had a scale in the graph, we might see that the y-intercept is, say, 5. It has an x-intercept. If we extend it over here, it might have an x-intercept, and that might be significant. It has a slope. Slope is rise over run. So between two graph points we can find a rise and a run, and we can specify a slope. So this is just one example. We could describe this graph as linear and increasing with a y-intercept of 5 and a slope of 0.7. Now there are other behaviors a graph can have. Not every graph is linear. Some things that increase faster and faster. We might say this is increasing at an increasing rate. We also say that it's concave up. Or we might have a graph that's decreasing faster and faster. We might say it's decreasing at an increasing rate, or we might say that it's decreasing and concave down. Okay. Here we have a summary of some of the behaviors that we might see for a graph. Okay? A graph could be, well, we're looking at the increasing, decreasing behavior graphs and the intercepts of the graph. This graph might be interpreted as, let's say the green graph here, as increasing and concave upward. Okay, concavity, one way to think of concavity, the concavity of my hand, if my hand is a cave and I'm looking out of the cave, I'm looking in the direction of the concavity. Well, if this is a cave here and I'm looking out of the cave, I'm looking in the upward as opposed to the downward direction. I might actually be looking out this way, but it's definitely upward and not downward. We have here a function that's increasing at a constant rate, as opposed to this function, which is increasing and concave up, increasing at an increasing rate, increasing faster and faster. This is increasing, but it doesn't increase any faster or any slower at any point. It keeps increasing at a constant rate, and that's a linear function, and of course it's increasing. So we might describe this function as an increasing linear function, or an increasing function which is increasing at a constant rate. The red graph here would be a graph that's increasing, but it's concave down. It continues increasing. It never stops increasing, at least not in the part of the picture we see. It might very possibly level off and start decreasing out here someplace, and we'd have to describe that. But this graph is increasing and concave down, or we might say increasing at a decreasing rate. Okay, we want to specify the x and y intercepts of a graph. For example, we would say that the graph intercepts the x-axis at x equals 7. That would be a statement of intercept. We want to use that kind of language in describing graphs. Now we've seen examples of functions that are increasing at an increasing rate and increasing at a decreasing rate and increasing at a constant rate. Here are a few more. Here's a function that's decreasing, but the rate at which it's decreasing is getting less and less, so we might say decreasing at a decreasing rate. More properly, we'd say decreasing and concave upward. So this graph is decreasing and concave upward. If we're looking out of the cave, we're looking in the upward direction. This graph is decreasing at a constant rate, and this graph is decreasing at an increasing rate, or decreasing and concave down. Another important characteristic of many graphs is asymptotes. An asymptote is a straight line that the graph approaches more and more closely. Not only does it approach more and more closely, there's no limit to how close it approaches, but it never touches the asymptote. It gets as close as you might wish to choose, but it doesn't ever touch the graph. You can't choose a closeness that this graph doesn't eventually exceed. Then we have an asymptote. Okay, so here we have the purple graph. Here we have the graph approaching a vertical asymptote, a vertical straight line. Here we have the green graph approaching a horizontal asymptote, a horizontal straight line. And here we have the other end of the purple graph approaching a slant asymptote, a straight line that's neither horizontal nor vertical. Those are basically the three types of asymptotes we can see. Now, if a line approaches a slant asymptote, you want to tell us what that line, if the graph approaches a slant asymptote, you want to tell us what line it approaches, what line it's asymptotic to. And you would specify that line by, say, its slope and its y-intercept, or its equation. If we approach a vertical asymptote, we just want to say that it approaches a vertical asymptote, and we want to give the x-coordinate, the x-intercept of that asymptote. So let's say this is x equals 2 here, if this line was extended down. So this line might be x equals 2. So we approach the x equals 2 line as a vertical asymptote. This is how you'd want to communicate that. Or if this horizontal line here is y equals 4, let's say y is 4 all along this line, then the line is y equals 4. Then we'd say we approach the horizontal asymptote y equals 4 as x approaches infinity, or as x gets large. Okay? So in general, we want to specify the slope and intercepts of an asymptote.